Hi, welcome to video on control systems. So in this video we'll see a specific root locus problem where we'll be estimating the gain for a desired specification of damping ratio of certain value. So this is the problem what we have. So we are supposed to plot the root locus for a given open loop transfer function in the feedback HFS and GFS. And we are asked to locate the closed loop poles such that the root loci has dominant poles having a damping ratio of 0.5. So damping ratio is supposed to be 0.5. So we are also supposed to find the value of corresponding value of k. So we'll just do this problem both using the graph as well as using 20sim simulator and try to verify the values. This is a transfer function that is given GFS into HFS is given by k into there is a 0 at -9 and there is a pole at origin, and there are two complex poles. Upon finding the complex position, it is -2 plus or minus j2.64. So this is the S-plane representation of poles and zeros, which is having a pole at origin 0 at -9 and two complex poles. So since we have three poles and a 0, the number of asymptotes are 2, the angle of asymptotes are 90 degree and 270. The centroid actually comes onto the right hand side of the S-plane. So since it is 4.5, it's situated here with asymptote 1 at 90 degree, other is at 270 degree. So let us see how does this root loci will move from open loop position. And we know that since we have a complex poles, so we are supposed to find the angle of departure for this. So angle of departure for root loci, which is given over here, which is -2 plus of j2.64. So it is given by theta d is equal to 180 plus phi, where phi is given by summation of theta z minus summation of theta p. So summation of theta z is nothing but we have only 1 0. So theta z1 is this value, which is nothing but 20.6 degrees, so which is approximately over here. And then since there are two poles except this one, so the angle subtended by these two poles onto this particular point is given by one is theta p1, other is theta p2. Theta p1 is actually 180 whole degree minus of this quantity, which is nothing but tan inverse of 2.64 by 2. So and this overall angle comes out to be 270 degrees. So we end up with the angle of departure. Upon substituting all these values onto this equation of theta d, we are getting it as -16 degree as the angle of departure for this particular complex pole position. If you consider this, it will be plus 16 degree because it always symmetric about the real axis. We'll see the exact departure angles on the plot. And since we know that since the asymptote lies on the right hand side of this plane and the angle is at -16 degree, it has to cross the imaginary axis at some point. So since it is crossing the imaginary axis, we are supposed to find out the point of intersection of root loci with the imaginary axis. That can be found by writing the characteristic equation, writing the roots array. So this is the characteristic equation for the given problem. So we have constructed a roots array. So upon solving the roots array, it is found that the k margin, that is the value of k for system to be marginally stable, is coming out to be 8.8. So from which we can find out what is the auxiliary equation, which is 4a square plus 9 into k margin. From this we can actually find out what is the point at which it is going to cross the imaginary axis. So roots of the auxiliary equation happens to be plus or minus j4.4. This is the point at which it crosses the imaginary axis. So we have what is the angle of departure, we know what is the point at which it is going to intersect the imaginary axis. Then we can now plot the root locus. Okay, this is the root locus of the same transfer function in 20sim simulator. You can see the angle is almost -16 degree and it is crossing somewhere here. You can see this magnitude is 5 and this is almost close to 4.44, and you can see here the angle is plus 16 degree and it is also crossing minus 4.44. so this is in 20 sim simulator. So what is asked now is we are supposed to find the dominant closed poles so that zeta is equal to 0.5. You can see there are some lines that are put out here in 20 sim simulator. These are all the lines corresponding to zeta value. This is 0.1, 0.5, 0.2, 0.3, 0.4, 0.5. So this 0.1 actually corresponds to cos inverse of 0.1 that is measured from this angle from here. So cos inverse of 0.1 whatever comes is this angle. This is cos inverse of 0.2. So likewise we are looking for a zeta of 0.5. So we are looking at this particular dotted line which corresponds to zeta of 0.5. So that's what we are trying to do here. Now since we are asked to estimate the value of k, so k is nothing but a unit distance from all poles. So you can see we have this is a point of intersection of this root loci with this 0.5 zeta line. This is actually cos inverse of 0.5 happens to be 60 degree. This is actually a 60 degree line measuring from this as the reference from here to here it is 60 degree. So that is what is that line indicating. Now what we are trying to do is we are join all the poles and zeros to this particular point of intersection of root loci with this 60 degree line which corresponds to zeta is equal to 0.5. You can see we are mentioning this distance as a from this 0 to this point of intersection, and this pole is having a distance from here to here as b, this is c, this is d. So you can actually find out the value of k as b into c into d divided by a, because a is the distance, unit distance from 0 to pole, and the remaining BCDs are the distance from different poles to the point of intersection. Because point of intersection is over here, so we are measuring the actual distances from each of the poles and zeros, and we are taking the product of all poles and zeros. It is product of poles by zeros. Since we have more number of poles, it is 3 terms in the numerator and we have only 1 zero. Assume that if when you don't have any zeros, you can put this as 1 here. So it is not 0, you have to put it as 1. So looking at those values, if you can see that this is cos inverse of zeta, this is actual plot. So this is 60 degree line. So you can see we are joining this intersection point to this 0, this pole, and the second pole and the third pole. You can see this is first pole, second pole, and third pole, and this is 0. You can see the distance from this 0 to this point of intersection is 7.8 centimeters, because here we have taken 1 unit is equal to 1 centimeter. So and then b happens to be 5.3 centimeter. 3 is corresponding to c, and we have 0.5 as the distance from this complex pole to this point of intersection. Upon solving this, we are getting it as 1.09. The dominant pole is this has to be slightly changed. This is not minus 1.8. This can be, you can see since this is minus 2, this can be minus 1.5 here. So by mistake it is written as minus 1.8. This is actually minus 1.5. Maybe in 20 simulator we can actually know what is the position, because we can actually place that cursor exactly on that point of intersection. This actually dominant poles are minus 1.5 plus or minus j 2.5. This is approximately on the graph. It's a human calculation, and then we can actually know what are the values. Okay, this is what is we are trying to identify dominant poles here. If we can actually see the linear value of k, this is a zoomed version of this. You can see the value of k is coming out to be 0.95, which is exactly, we get it almost close to 0.95, which is 1.0. They are almost close. You can see the dominant poles are one is okay, so here you can see this is 2.58 and this is minus 1.52. So this is the real part of it, which is minus 1.5, and the imaginary parts are okay, plus j5 2.58 and minus j 2.58. We almost got it as plus or minus j 2.5. So of course there in simulation you can exactly get the values as minus 1.52 can see this is minus 1.52 plus or minus j2.58. so this is exactly the location of the dominant poles for a value of zeta is equal to 0.5, which results in an angle of 60 degree, and the corresponding value of k at this point is actually close to 1, which is 0.95 here, 0.95. We can actually do, of course, we can also verify what is the value of this here. This will be almost very close to 4.4. So this way we can able to find the value of k for a given value of zeta, because zeta is the one which decides the overshoot of the system. So for this given problem, so we need to first plot the root locus and then draw a line corresponding to 60 degree line. So this is that 60 degree line, which is exactly corresponding to 0.5 in this 20 sim simulator. Otherwise, what we are doing here is we are drawing a line corresponding to 60 degree, and this is a point of intersection of that 60 degree line with this root locus. Then you join all points, all zeros and poles to this. Then k is given by b into c into d by a in this particular problem, and you can exactly locate the pole position. Now in this case it is minus 1.5. This is actually minus 1.5 and plus or minus j 2.5, which is exactly true here in your simulation. So this way we can able to solve the value of k for a given specification. In this particular case it is the value of damping ratio.